Are you ready to explode your mind? Welcome to the future of creation.
When running an industrial machine at high speeds, the physical stress is immense. You are throwing heavy mechanical arms and cutting tools across a workspace, and you need them to stop on an exact micromillimeter, instantly, hundreds of times an hour. Legacy open-loop systems, like older stepper or brush DC motors, struggle with this mechanical reality. They receive a command to move, but they have no way to verify if the physical hardware actually arrived at the correct destination. This chart illustrates the core problem, coasting distance. When the controller tells an open-loop motor to stop, the physical momentum of the toolhead keeps it moving slightly past the target. That overtravel introduces a permanent error margin into the machining process. To compensate for that lack of absolute control, engineers have to program their machines to operate slower. They ramp down the speed long before the target position to minimize the coasting effect, which extends cycle times and drags out production schedules. Relying on a system that guesses its final position guarantees surface finish defects on tight tolerance parts and ultimately leads to unpredictable machine downtime. The practical fix for this error margin is upgrading the machine tool to a closed-loop AC servo system. A closed-loop motor continuously reports its exact position to the amplifier. The deviation counter subtracts the actual feedback pulses from the incoming command pulses. This creates a speed command, driving the positioning error to exactly 0. However, dropping a massive, high-powered AC servo into a chassis doesn't automatically optimize your machine. If the motor's rotor inertia is too aggressive for the mechanical payload it's trying to push, the system fights itself. You end up with tuning instability, heavy vibrations, and potential damage to the drivetrain. A successful retrofit requires matching the specific physics of the cutting load to the right motor. For the industry-standard FANUC Alpha series, that means decoding their catalog to understand exactly how different models behave on the floor. Before looking at specific models, we have to look at the shared foundational engineering inside every FANUC Alpha series motor. At the core of the rotor, FANUC utilizes high-strength neodymium ferrite magnets arranged in a highly specialized magnetic pole geometry. This specific layout generates an intensely high magnetic flux density while actively suppressing torque ripple. As the rotor turns, the magnetic pole remains perfectly uniform, eliminating the microstutters you get in lower-end servo designs. This dense, uniform power requires advanced software and capable amplifiers to calculate adjustments in milliseconds, ensuring the axis remains completely stable even when the cutting tool hits an unexpected hard spot in the metal. But generating ultra-smooth rotation in a vacuum doesn't matter if the reality of the manufacturing floor destroys the motor's internal electronics. To protect that magnetic core, FANUC wraps the internal components using a unique stator seal design and heavily insulated waterproof connectors. This physical sealing allows the motors to be mounted directly inside the primary machining zone, operating continuously while blasted by liquid coolant and metal chips. Once the physical hardware is secured, the next limitation is electronic. The motor relies entirely on its built-in optical pulse coder to track its exact location. This chart maps available resolutions from 8,192 divisions per revolution through 65,000 up to an extreme 1 million pulses. You also choose data storage. Incremental encoders require homing routines at startup. Absolute encoders use battery backups to permanently remember their exact position. Specifying a 1 million pulse absolute encoder for a simple automated conveyor belt wastes your budget and overloads the CNC controller with raw positional data it doesn't need to do the job. Once you understand the baseline hardware, you hit the primary decision point in the catalog, choosing between the Alpha M series and the Alpha L series. The Alpha M series is built with an intermediate rotor inertia profile. Because the rotor possesses moderate physical mass, the Alpha M can safely translate electrical current into aggressive acceleration and massive output torque. It is designed for feed axes that are constantly starting, stopping, and rapidly changing direction. The Alpha L series takes the opposite approach. Its internal geometry is engineered specifically to minimize heat generation during sustained, high-speed rotation. You are making a direct trade-off. By selecting the Alpha L, you sacrifice some of that immediate, punchy acceleration, but you guarantee the motor won't suffer from thermal throttling during long, continuous production runs. The physical mass and shape of the rotor itself dictates whether your machine will excel at rapid repositioning or sustained, heavy, continuous work. We can map these trade-offs into a straightforward decision framework. If your payload is a dynamic feed axis, like a robotic arm requiring aggressive direction changes, you route directly to the Alpha M series. If the application involves high-speed spindles or a continuous rolling process where thermal buildup is the primary threat, you specify the Alpha L series to manage that heat over long shifts. Things get highly specific when you are tasked with retrofitting older, aging assembly lines that are already built around legacy hardware. If a machine is currently running the older FANUC Alpha 3 or Alpha 6, integrators can specify the new Alpha M3 or Alpha M6. The mounting dimensions are identical, allowing you to drop the new closed-loop technology directly onto the chassis without re-engineering the physical brackets. Upgrading an industrial machine tool works when you accurately map the mechanical load profile to the correct motor family. There is one final variable to account for: the time it takes for your line to physically start working after you flip the power switch. If you have an access that needs to resume operation instantly after a power cycle without taking the time to slowly perform a reference homing routine, you have to specify the absolute encoder package. That instant startup convenience costs you permanent maintenance overhead. You will have to monitor and replace the physical battery backup units on schedule, or risk a total loss of the machine's positional data. Achieving perfect closed-loop precision requires balancing these physical limits. You are negotiating between inertia profiles, heat dissipation, and the data processing limits of your controllers. Optimizing a multi-axis CNC machine or robotic cell means ignoring broad marketing claims and matching the exact physical properties of the servomotor to the harsh realities of your specific manufacturing floor.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.